It's time for another episode of What is Dark Matter? And so this week we're focusing on the Axion, which is one of these proposed particles. It's been around for a long time to solve other issues in quantum mechanics, but actually turns out to be a pretty nice candidate to explain a lot of the observations that have been made about dark matter. And some fairly interesting tests and experiments have been made at large scale structures in the universe to try and sense if it is axions that are causing this. So to help me better understand both axions and the kinds of experiments that are being done today is Dr. Keir Rogers. He is a cosmologist at the Dunlap Institute for Astronomy and Astrophysics. And first, he helps me understand just like what axions are, and I'm not sure I completely get it yet, but we're getting closer. Give me a few more interviews and I might have this in my head. But also then, what are the kind of large-scale surveys that astronomers are doing to try to understand it? And I guess more importantly, what the next round of mega telescopes are going to do to help really provide precise observations that should, if not explain it, narrow down what it isn't. So enjoy this conversation with Dr. Keir Rogers, and hopefully together we will understand this better and better over time. I've been following this story of dark matter for a long time, and, there have been a lot of proposals for what it is, WIMPs, MOND, axions, all of these ideas. And I guess they're all mysteries, but I'm trying to sort of understand the parameter space of each one of these mystery possible theory explanations. And the one that I'm kind of obsessed with right now is axions. So I guess for people who have, they've heard, everyone, all my audience will have heard the term, but they won't necessarily know what exactly it is. So can you provide just a great definition for what an axion is?
Sure. So an axion is it's a kind of subatomic particle. So like a WIMP, it would be some new species of particle that would exist. And it can be quite a generic thing. So it can mean different things to different people in a sense. But what really defines it is that it is some field. So it's some value, some quantity that has a value everywhere in space. And it has an axial degree of freedom. And so that's where the name axion comes from. And so it has some value between 0 and 360 degrees.
All right, I want to
I
want to separate those sort of like into two pieces. So I want to start with the first part, which is that it is field-like. And I think we sort of think about this idea of quantum mechanics, that what we think are particles are actually, in many cases, fields that stretch across the universe, and they happen to have a probability of being in some location, but there's a slight chance that this electron that you're using for your computer is actually in Andromeda right now.
Exactly, yeah.
But I guess, how does it differ? Like, if dark matter is some kind of particle, wouldn't you expect it to be some kind of potential field just by default, because that's what particles can be?
Yes. So the idea is that you could have a field description of almost any dark matter candidate. And so what distinguishes an axion is the potential energy in which that field exists. And it's the fact that that has an axial degree of freedom. And that's quite generic. Yeah.
So, do we have a comparison? Like, are there other particles that we're very familiar with that are absolutely nailed down that have similar levels of energy?
Not really, right? So to be more specific, the particular type of axions that we're talking about are these extremely light axions, these ultralight axions. And they're really like nothing else that we know for certain exists. And that's because it's not just that they have an axial degree of freedom, but they have these extremely low particle masses.
Got it. Okay. All right. Yeah. And let's talk about the second part, this axial degree of freedom. So what does that mean?
So it's just really to say that in the early universe, this field, whatever exactly that is physically, has some value and it has some value between 0 and 360 degrees. And so in the beginning of the universe, it could have any of those values. And then the idea is that the symmetry in that axial degree of freedom will break at some point. And then that will drive the value to a particular value. It'll then acquire a particular value, but you don't have to choose that value. It happens automatically through the dynamics of that field.
I mean, I'm trying to think of an analogy, like polarity. Does that kind of get you partway there? I mean, I know that, when you're talking about particle physics, sometimes it's literally impossible to come up with an analogy that makes sense in words. You sit down with another particle physicist and you write some math on a piece of paper and you hand it over and look at the math and go, yeah, totally, I get that. And yet, you've asked them to try and explain it. They can't because it's math. And yet you can find these particles based on the math. So,
this is the challenge, right, of all of us to convey it, right, and for us to understand it as well, right, in physical terms as well. So the way to think about it, right, is that you have this hat-shaped potential. So it's like a sombrero hat, and the field is sitting in the rim of that hat, and it's just rolling around that hat. It could have any value you like around that rim. And then it's as if someone suddenly just put the hat on its side, and then the little ball you have in there, which is your axion field, rolls towards the bottom of the potential well that you've created.
And I'm assuming that then gives you candidates, places you could look, places to actually make observations that could confirm the theory.
Yes, so that dynamics is key to how you would then detect axions. So in particular, when these axions are rolling around the bottom, so the idea is that they roll down this hat. When they get to the bottom, they will initially slightly overshoot, so then they'll roll back, and then they're essentially oscillating around the bottom of that hat. And it's in that period that they're behaving like dark matter. And so that's when we can look for them as a dark matter candidate.
Got it. Okay. All right. Okay. So then, I think, a lot of these possible candidates for dark matter have been, very difficult to try and gather any kind of observational evidence. And so far, nothing has worked. I mean, we have scans of the universe at the larger scales. We have particle detectors in mines in Sudbury, Ontario. Maybe you've even visited it. There are all these places where people are looking. So what is sort of, I guess, at the largest scale and at the small scale, the ways that observers are looking for axions?
Yeah. So there's a huge number of ways, is the truth. And there's been this big explosion in interest for axions, and that means that people have come up with many different ways to detect these particles. On the direct detection side, so the sort of equivalent of those underground detectors, you have instruments like things called haloscopes and helioscopes, and these are fundamentally exploiting the fact that because this axion is oscillating, and in particular, it'll have a coupling to light, to radiation. And so you hope to sort of exploit the fact that you could resonantly convert these axions into photons and then detect the photons that would be produced. And then on the cosmic side, which is specifically what I work on, when we consider these very light axions, that's when they're fuzzy. And so then you would see these very distinctive wave-like features in the large-scale structure of the universe. And there's a complementarity between those two different approaches.
Right. And I know there are like things that look like sort of giant tubes that they have at like CERN and things like that, where they're trying to measure, like if axions are coming in, they're passing through more material than should be possible by any particle. And they are making these conversions, as you say, to photons and kind of appearing in the detectors at places where photons shouldn't be appearing, giving some kind of indication that this particle is there. But so let's talk about these cosmological searches. So what, I guess, like what is the best way to just like, what tool would you use to sort of scan the universe? Are you looking for gravitational lensing? Are you looking for some kind of particle emission? What are you looking for?
Yes. So, again, there are different ways that you can look. I think with these extremely light, ultralight axions, these fuzzy axions, you basically want to measure the distribution of all the dark matter in the universe. And if you could do that, you could see if it's made of these axions or partially made of these axions, you would see very distinctive wave-like features in how the dark matter is distributed on large scales in the universe. And if you saw that, that would be a real smoking gun signature that it is made of these axion particles. And then the challenge we always face is that the dark matter is almost invisible. And so we have to indirectly trace its distribution through things we can see.
Right. So how big of a volume of space would you want to be looking at to get some kind of statistical significance?
Yeah, so this actually partly depends on the mass of the axion that you're looking for. So the idea is that by the quantum uncertainty principle, the lighter the particle gets, the longer its wavelength gets. And the longer its wavelength is, then you need a larger volume of the universe to see enough of these wave imprints to be confident that you've detected something.
And so if you were able to say view, I mean, again, like, is it 1 billion light years on a side? Is it like how big of a cube do you think you would be wanting to look at? Because I want to sort of talk about the telescopes that can get us there. So, which are about to launch or
so
about to roll out, right?
I always struggle with light years because in cosmology we measure it in parsecs and megaparsecs.
Yeah, how many megaparsecs? Go ahead, it's all right. We can. I'll convert for you.
So the larger surveys that we use, and so some of the data that we used in this work that we've been doing comes from the baryon oscillation spectroscopic survey, and that's surveying on the order of a cubic gigaparsec. So it's a really large scale, large volume survey with up to 1 million galaxies, the positions of 1 million galaxies mapped, throughout space, and we essentially, take all that information and look for these wave-like features and how the positions of galaxies are tracing the large-scale distribution of the underlying dark matter.
Right. And so, what did you find?
So what we found is, so the first starting point is that when we measure how the dark matter is distributed through different ways that we can indirectly trace it, we currently have a discrepancy in how clumpy, so how large the fluctuations are in the amount of dark matter as measured from different probes. And in particular, from when we measure it from the cosmic microwave background, which is this light, this relic light from the Big Bang that we see today, and when we measure the distribution of dark matter more locally and more directly through these large volume surveys. And so the main thing that we found is that you can account for this discrepancy if the dark matter is partially made of these extremely light axion particles.
It's interesting that you say if it's partially made. Because this is the answer that I seem to be getting from astronomers at this point is that it seems more likely, or it seems interesting that dark matter, like missing regular matter, is probably made up of a whole bunch of stuff. Like it could be some axions, it could be it could be a little bit of MOND, it could be a little bit of WIMPs. Like you could add it all together, and this is why it's maybe so tricky to come up with a clear signal for any one of them, because they're all mashed in there. Is that sort of the suspicion that you're getting as well?
That is very much my suspicion, and it might explain to an extent why we haven't seen anything. Because so far we've been considering, which is a good starting point, these simplest cases where the dark sector is just one single species of particle. But it's increasingly likely, like you say, in the same way as the standard model of particle physics is extremely complex, that the dark sector could be made of many different types of massive particle, light particle, or even dark radiation as well. And so a key thing in our analysis is that we don't restrict ourselves to these very simplest cases where the dark matter is just made of one thing, but we allow for a mixture of different types of particle.
Right. But that's got to be rough. I mean, if there's 10 times as much mass out there of dark matter as of regular matter, and whatever multiplication of dark energy compared to regular energy, and if the standard model is such a diverse group of particles, maybe it's 10 times more particles, right?
Right. So you're right. You can go down a route where you make it increasingly complex. But I think it's reasonable. The approach we take is we say, hey, look, there could be this one new type of particle, and then we allow that to vary as a fraction of the total. And we're just basically measuring what quantity of the dark matter could sit in one species of a new particle, and we don't worry about exactly what the rest of it is at the moment. We just concentrate on each component at once.
Or at least, I guess, being able to rule out things. So do you think that you've been able to rule out some ideas at this point?
So, yes. So one of the things that we find is that we know that the dark matter cannot be entirely made of one of these very light axions. But what we do find is that it can be made of a mixture of these things. And then more than that, if that is the case, it would address this other problem that we have in cosmology, which is this clumpiness problem. And so, we set out looking for what could the dark matter be, because it's this huge problem, a long-standing problem, and it will hopefully, if we can gain some insight into what it is, it can lead us to answer more fundamental questions about the origin and the future of the universe. But in the process, we'd like to sort of mop up other problems that we have along the way. So the fact that it can also potentially address this clumpiness problem, is an added benefit to this idea.
And can we talk a bit more about this clumpiness problem? What is it?
Yeah. So essentially what we do in cosmology is we're measuring the large-scale distribution of the dark matter as a function of wavelength. So we look at it when averaged over large scales or smaller scales, but also as a function of time, in that we can see how the dark matter was distributed at different stages through the history of the universe. And when we measure how, and so the key point here is that the dark matter is not evenly distributed, right? So there are parts of space that have more dark matter than average, and parts of space that has less dark matter than average. And that means that there's parts of space that have more galaxies on average and parts of space that have fewer, these galaxy clusters and these galaxy voids. And what we refer to as clumpiness is essentially just a number that we measure, which is the amplitude of the fluctuations in the amount of dark matter that there is. And so the problem is that when we measure that more directly, so when we actually look at the local dark matter distribution, we get this lower value than what we more indirectly infer from the cosmic microwave background. And we currently have this roughly 3 sigma discrepancy between these two values that we infer.
Right. Which is significant. I mean, 3 sigma is, what's that, like 90%-ish? Trying to think what that,
yeah, so it's I think it's 99.7%.
Okay. Yeah, all right.
Yeah.
Which
so it doesn't hit
like
that 5 sigma real absolute crisis that we have with the Hubble tension, which I'm sure you've covered on your channel.
Yes, of course.
But it is sort of approaching that, and I think the key reason to worry about it is that we're in an interesting stage in cosmology where we do have lots of very precise and accurate ways of measuring the dark matter distribution. And what we'd like to do is combine all the information that we have. So we'd like to take the information from the CMB, from galaxy clustering, from galaxy lensing, and combine all this information. And to do that in a robust and confident way, you don't want these 3 sigma differences between these values. So you'd like to find theoretical models where you improve the consistency between these data. And so that was one of the real key motivations to considering these Axion models.
And do you think there's a connection? I mean, maybe we're moving the speculation mode here, but that the measurements that you're making on clumpiness in the cosmic microwave background radiation, and also the Hubble constant that astronomers are measuring in the CMB, are different from more local, later measurements. That's weird that both are seem to be happening. Is the crisis spilling out?
There's no clear evidence that there's necessarily any connection between the two. There are some models that do try to explain both simultaneously, and they do typically come from the Axion sector. So the most popular new physics solution to the Hubble crisis is something called early dark energy. And this is the idea that you had a burst of accelerated expansion sometime before the CMB was released. And in fact, it's a kind of axion-like particle that would cause that early dark energy to exist. And so there are a few ideas out there linking axion solutions to the clumpiness problem and axion solutions to the Hubble crisis into a single model. Now, in my personal taste, the early dark energy solutions are a little bit contrived in that we have no reason to expect that early dark energy exists if it wasn't for the Hubble crisis, whereas the clumpiness problem being addressed by axions is a neater solution, probably because we're just explaining what dark matter is, and we know that dark matter has to exist. So the fact that something that we know must exist could be associated with a discrepancy is theoretically more pleasing.
I see. So it's not as if somebody was investigating the potential of axions and they said, if these things were present in the early universe, you should measure a difference in the Hubble constant when you look at the CMB compared to, right? And you're making this prediction. I mean, that's the gold standard of science, is that you make this prediction and then people go out and make the observation and they go like, you're right, we found it. And that's, someone instead is going, yes. Well, I think if the axions could be dark matter, then that could explain it. And yeah, post hoc rationalization can get you pretty far if you needed to.
Yes.
So I guess let's talk about how this gets better, because there is a range of really interesting telescopes coming online, both ground and space-based. We've got Vera Rubin coming online next year. We've got Nancy Grace Roman launching in 2027. We've got Euclid launching tomorrow. Mm-hmm. So all 3 of these will contribute, I'm assuming, right?
Absolutely, yes. So these large-scale experiments, and in the field we call these the stage 4 experiments. We've gone through these 3 stages of sensitivity in how well we can measure essentially the distribution of dark matter. And we're now sort of upping it up by another order of magnitude in terms of number of objects and how often we observe these objects. And we have these ground-based telescopes and these space telescopes that are going to really transform, the number of objects, the volume of the universe that we can survey, and also hopefully the density as well. It's harder to measure these sort of small scale fluctuations. That also needs some theoretical work. And what I'd also throw into there is the cosmic microwave background experiments. They're also entering the stage 3.5, stage 4 era. So there's an experiment that I'm involved in, which is just wrapping up, called the Atacama Cosmology Telescope. And that will be transitioning into the Simons Observatory, which is a network of ground-based microwave telescopes that are also going to provide a huge amount of information about the dark matter distribution.
Right. And what would you be looking for, like when you get access? Let's imagine that Vera Rubin and Euclid and Nancy Grace Roman all come online simultaneously and you
Mm.
get to open up one folder of data, what are you going to be
Mhm.
looking for to try and understand this situation better?
Yeah. So the final piece of information that we need to really, assess how important this clumpiness problem is and the extent to which Axions could solve this problem is a combination of this galaxy clustering information and the galaxy lensing information. So on the one hand, we just essentially measure the positions of galaxies through space, and then we measure how clustered they are, and then that is a trace of how clustered dark matter is. And then because we're taking images of these galaxies, we have this sort of extra information, which is this gravitational lensing effect. So the fact that the light from the galaxy on its path to us gets bent by any intervening dark matter. This is a prediction of general relativity. And this is another measure of the distribution of the dark matter between where the real galaxy sits and us as the observer. And so we have two independent probes of the dark matter, and then we can also cross-correlate those two pieces of information. So we call it the 3x2 data set. So we have these 2-point correlation functions, and we have 3 of them that we can use. And that's the
Right.
kind of gold standard product of these photometric galaxy surveys.
And so back to that, that level of sigma, do you think that you would get with those instruments, get to that sort of 5 sigma gold standard measurement at this point?
Yes, so it's not exactly clear yet. Some of the forecasting work to predict what we'll get from these surveys is ongoing, but I do anticipate we will know or not whether we really reach this gold standard, and either way, we're going to learn something about the nature of the dark matter. Right? We can still test. Even if there is no discrepancy that holds up, we can still test whether these axions exist or indeed other flavors of dark matter, like warm dark matter or self-interacting dark matter as well. So it's guaranteed to give us, tell us something about the fundamental nature of what the dark matter is made of.
How do the cosmological searches for this help with the experimenters who are building these instruments in the lab?
Yes. So there's a definite complementarity between the two. And I think the big picture here is that we have historically, and for good reasons, put a lot of effort into searching for the WIMP, for those underground experiments that you mentioned, and also at colliders like the Large Hadron Collider. And now there's this new energy to consider sort of, in addition to the WIMP, well-motivated alternatives like Axions. So they're building these new experiments like these haloscopes and helioscopes that we talked about before. And for these ultralight Axions, you need other new types of technology. So there are things that exploit sort of quantum clock technology. So there's experiments like MAGIS at Fermilab that, if these ultralight Axions exist, we'll be able to see the oscillatory patterns in their quantum clocks from these extremely light Axions. And if I could throw in another way of looking for these particles, is something called pulsar timing arrays. So that is an astronomical observable. We just had exciting news
that you're bringing this
yesterday.
up. Yeah.
Exactly. And so if the dark matter is made of these extremely light Axions, that field is oscillating around the bottom of that hat, then essentially the density of the dark matter in the Milky Way would be oscillating with time. The light from these pulsars would be moving through that oscillating potential, and you would see an oscillatory pattern in the timing measurements. And so we have all these different prongs, different ways of attacking, and looking for these different kinds of dark matter.
And so, like the next generation, say, space-based gravitational wave observatories like LISA would also help you get an idea about this.
Absolutely. So in particular, LISA fills this gap, right? So you have ground-based gravitational wave interferometers like LIGO that are probing quite high frequency oscillations, pulsar timing arrays which are probing these extremely low frequency oscillations. And then LISA just fills that intermediate gap, and it's a sort of missing window in direct detection for these ultralight axions that LISA should be able to fill. But we might have to wait maybe 10, 20 years till we...
right, yeah, mid-2030s. It still feels like forever. There's this interesting cycle in astronomy, and maybe it's in all of science, wherever you need big instruments, where you have this tantalizing hint that this thing exists, and then scientists, suggest the layout of the machine that will help them get to the next level. And as you say, you bring in an order of magnitude more powerful instrument to bear, and then you get that next series of observations. So do you think this new round of machines, the telescopes we've talked about, as well as the various labs, that the answer for what is dark matter will start to fall out of it as a result?
I really hope so. I think there is a lot of reason to be there is reason to be excited right now, and it's because of this sort of shift, right, away from a heavy focus on WIMPs to, an appreciation that it could be other things. Again, like we were saying earlier, that it could be more than one thing. And there's all sorts of new technologies that are just probing this sort of wild west of the dark matter model space and parameter space that, have extremely good theoretical motivations, dating back to the 70s and 80s in the case of Axions, but were, it seems, somewhat neglected experimentally. And now we just have this energy, right, in building new types of detector, and from the astrophysics side of things, reconsidering how our astronomical data can test these different models. And so we're now considering such a variety of dark matter candidates that we're definitely going to learn something. And in the dark matter game, you do still you learn a lot by exclusion. So, and that's how we have progressed so far, right? That we gradually exclude, we knock out the candidates, and we slowly, narrow down on what is the most feasible.
Yeah, it's an excruciating way to make progress. Instead of figuring out what something is, you're having to figure out what it isn't, but it is still progress. Let's say that this next round of instruments, maybe narrows the field a little bit, but doesn't really give you a definitive, when I think about, say, the Large Hadron Collider, right? Its job was to find the Higgs boson with ludicrous levels of sigma, and it did. Like, boom, right on schedule. We found it. It's the missing piece of the standard model. We're done. But it doesn't feel like with these instruments, there's that level of certainty for what it is that you're even looking for. So we're sort of, it's a bit more of a, I don't know, like a fuzzy outcome. It could go so many ways still. And I wonder, let's say that
yeah.
Go ahead.
Well, there are particular targets, right? So I started this by saying, well, the Axion's something quite generic. It's sort of this generic feature of a field and a particle, but there are particular parts or particular flavors of Axion that are particularly well motivated. So there's the QCD Axion. So that's the original Axion that was motivated to explain the strong CP problem in the standard model of particle physics, which is a sort of discrepancy in our quantum description of nuclear matter. And if the Axion exists, it explains that problem. And so, again, as I was saying earlier, it's nice when your dark matter candidate mops up other issues that you have within your theoretical landscape. And so that QCD Axion is a key target of those haloscope and helioscope experiments. And they have particular theoretical predictions for the mass of the particle and its coupling to radiation. So there are key targets that you're focusing there. And for these ultralight axions, there are particular parts of parameter space that are particularly motivated from string theory that are the particular masses and densities of these particles that we want to target. And those two targets are within reach within the next 10 to 15 years. So there is this broader landscape, but there are also particular targets that we are focused on reaching.
And if there was like, if someone asked you to design the experiment or instrument specifically to look for the kinds of results that you're hoping to find, what would that look like, do you think?
It might be actually the Rubin telescope.
Okay, but that's fine.
Yeah.
You get the Rubin telescope. So what is the super version of the Rubin telescope that you would want that would specialize in what you're looking for?
So I think the new frontier in this then becomes high redshift. So, the Rubin telescope and also Roman and Euclid to an extent are going to probe, relatively late times in the universe. So redshifts up to around 2 or 3, which is the last few billion years. But 21 centimeter observations, so observations of the 21 centimeter wavelength photons from neutral hydrogen right at the beginning of the universe, so not long after the CMB was released, we're going to start being able to detect beyond the next decade. And in fact, we have the first detections just coming online now. And so the key thing that will do, right, is it'll fill in this sort of unexplored part of the cosmic parameter space, which is what was happening to the dark matter distribution at the very beginning of the universe. And is it consistent with what we see at late times in the universe?
So want to be able to
we're guaranteed to see something unexpected there.
Right. So you want to be able to measure that clumpiness of this neutral hydrogen early on in the universe, and then sort of see how it evolves from what we know in the CMB to what we see in the more mature universe. So I guess
exactly. Yeah.
Is that a radio telescope? You want like a Vera Rubin, but it's a radio telescope in space, maybe?
Yeah. So it's there's things like these are radio telescopes, and the square kilometer array is what's coming. So that is a large array of these huge radio dishes, which covers in total on the order of a square kilometer of collecting area. And it's split across continents, right? It's going to be in its full phase in Australia and South Africa. And so, again, this is coming. This is sort of a little bit further down the line. But that, there's two approaches, right, to finding new things. It's when you have theoretical problems, but sometimes you just want to see some new bit of the universe that you didn't see before, and you will always see something unexpected. So I think from cosmology point of view, that is the sort of exciting long-term future.
Right. But again, you asked for a telescope that's already planned. And, I brought up my blank checkbook here. Yeah. So I'm trying to get a sense, like, is it a ground-based telescope? Is it a space-based telescope? Is it that it's looking for stuff like with Vera Rubin, it's looking for stuff that's changing. I mean, it's going to be imaging the entire sky night after night, but all those supernovae and asteroids zipping by don't really help you very much. You're looking at that, just sort of that deep view of the universe. So what is the perfect instrument to give us this answer? I guess to look at the 21 centimeter line, is it a giant radio telescope on the far side of the moon that's steering?
So people talk about going to the far side of the moon. The advantage of going to the far side of the moon is then you lose the Earth's ionosphere. Mm-hmm. So you have a lot of contamination in ground-based radio astronomy from the ionosphere on the Earth. And so if you go to the moon, you will lose this. However, you will still have all the radio emission coming from our own galaxy as well. And so there's some debate within the community about how useful going to the far side of the moon will be. I think it's going to happen, not least because I think the US wants to go to the far side of the moon and build a telescope there. So there's some motivation from that side as well. But, I'm not necessarily saying that is going to be the full solution. And so what I might push back a little bit on is it's not just new telescopes and new observations, but it's deeper theoretical understanding as well. And so arguably what limits a lot of what we're able to do at the moment is our ability to theoretically model all the observations that we have, and to be able to model the instruments and the telescopes, to model how the dark matter behaves in these non-cold and non-WIMP models, and also to worry about other things like astrophysics. So one of the key things to understanding the clumpiness problem is how strongly galaxies are expelling gas into the space around them, because this can also smooth out the dark matter distribution. And so there's a huge amount of theoretical and simulation, computer simulation work that needs to be done to interpret the observations that we have.
So it sounds like you don't know exactly what you need yet. So we'll put it in as a gift card, and then later on you can make the request for the blank check for the next generation telescope that'll get you the answers that you need. Keir, it was a pleasure to talk to you, and thank you so much for helping me understand this better. If people want to follow your work, what's the best place to do that?
You can go to my website. So my website is keirkwame.github.io. And there there's a link to all my papers and some of the sort of public-oriented articles that I've written as well.
Fantastic. And also, you did some lectures. There was like a cosmology during the COVID. You did some lectures there as well. So I know there's some presentations you've given to people who want to handle sort of a more technical bent on this. I sort of reviewed some of the stuff you've done online as well. So that's great. Yeah. All right. Well, thank you so much, and good luck. I hope we learn. I hope we find out what this is. But I also am enjoying the search. I think it's fun.
Great. Thanks, Fraser. I appreciate it.
All right. Take care. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I read every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltonan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Veribioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.